we talked last Thursday, I guess, about scalable clustering. We've been on this theme about how to do clustering at scale because we've been worried about some of the runtime associated with clustering algorithms. And we've looked at, so far, methods based on, let's see, so what are the methods we've seen? We've seen some basic core set type ideas. We've seen this whole issue of clustering the clustering, right? And the idea of clustering the clusters relates not just to compressing your data, but also to building a stream-based method. So just I want to review this idea because we're going to be sort of riffing off of it and going in a different direction today for another way of thinking about large-scale clustering. So the clustering on streams idea sort of came back to this more basic thing of how to, that you could sort of combine local clusterings into a larger cluster. So the idea was if you want to cluster a data set, so you first cluster sort of roughly into groups, right? And each group gets weighted, or each cluster center gets weighted by the number of points in it. So this takes points at P and outputs a new points at P prime with a weight function onto it, and then you cluster the clusters, or more precisely, you cluster the cluster centers. Right, so there's this two-step approach. So you do something crude here, and we had used the grid analogy to say, okay, you're kind of essentially snapping things to a grid, and then you're clustering the centers here. And of course, you don't have to use a grid, you can use something more general. The result works regardless. And if you can do this job well, then you can get a clustering algorithm out of it. And the point of this was that because you had this kind of hierarchical way of thinking about things, you first group into bits and then group the bits more, you could apply this over and over again. And that led to this nice idea for doing stream clustering, where you said, I have my data coming in along a stream, right? And I don't have a lot of memory. So I can't afford to store the entire data before I actually cluster it. So I'm going to first cluster the first bit. So I'm going to cluster the first section here and get some cluster centers there. And I'm going to cluster, and conceptually, I want to cluster the next section here, get some cluster centers here, and so on, right? But of course, I can't really do this, in one pass of the data and then do it again because I can't actually store all the data. So I'm going to first build the cluster hierarchy on this. Then when this new set comes in, I only retain all these points and that, which eventually gives me that. And then when I get the third set, once I do this, I can immediately take these points and start clustering these together. So I get a new set here. So I never maintain more than kind of one side of a tree of decompositions. And all of this works because of this idea that you can take clusters, click data, cluster it together, and then cluster those cluster centers and again. You lose error in the process. I mean, you incur extra error. That's the price you have to pay. But at least you can do it. And so that's the basic idea, that you build this kind of hierarchy, and so you end up with a tree. You can think of a tree, so you have nodes here, and then merging up here. So conceptually, this is what's happening, right? And then you're only maintaining sort of one side of this tree structure here to compute the entire. And this worked for stream clustering. All right. What we want to do today is go a little bit further to a different model of computation that is also of interest, that has become more interesting of late, actually, even more so than streaming, and is also a challenge for clustering, at least, well, has been. Now we're getting better ideas about it. And this is what is called the distributed model. And the setting for the distributed model is, something as simple as maybe having a bunch of data sitting on different cores, or a bunch of data sitting on different machines. So I have a bunch of machines, and each machine has its own collection of data. And you may have heard, in the past, I have talked about these models, and Jeff has talked about these models. So you have different nodes. You can think of them as nodes in a warehouse, or nodes across all over the US and different sites, whatever you want. But you have different nodes with their own access to data, and they want to compute something jointly. And there are, you can spend a lot of time worrying if you want about how they're connected together. I'm going to ignore all that. I assume there's some way for them to talk to each other, right? And for example, you could think of one node as being a dedicated server, and everyone just talks to the server, and the server communicates back with them. I'm going to not pay much more attention to how we do this. And if they want to compute something jointly across the union of these data sets, the easiest way to do this would be for all of them to send their data to one server. The server does all the work and tells them the answer. And that's maybe reasonable for some problems. But it's not reasonable if you have lots of data. Because you're spending a lot of time sending this data over, and this may not be much if it's a few gigabytes or even a few terabytes, but if you're having much more than that, then it's not. You would rather do something locally, send little bits of information to the server, and then continue with your algorithm. And so there's an abstraction. There are one of many, but there's one abstraction that has been somewhat useful in order to think about how to design efficient algorithms in this model. And that abstraction says, all we care about is communication. So notice in the stream model, we said all we care about is space. It was a bit of a lie. We don't just care about space, but that was the way we forced our algorithms to be interesting. Here we're saying all I care about is communication. In other words, I'm going to count the number of bits you send back and forth between the clients and the server, okay, in any direction. And my goal is to have sublinear communication. Okay? And again, why sublinear? The same reason we had sublinear space for a streaming algorithm. If you allow linear communication, then you can just send everything to one server. It's not interesting anymore. You're not really capturing the challenge of using communication efficiently. So saying that it has to be sublinear forces you to think a bit more creatively about what you're going to be sending over, because you can't just send over. And I'm not going to charge you for what you do on your individual node. I don't care how much space you use. I don't care how much time you use. And again, this is unrealistic. Of course, you actually do care in practice. But we're going to focus on this aspect to see how the algorithm design will work. And the actual algorithms will not end up being that hairy. They'll be fine. But they will be focusing mostly on this. Okay? So the model of computation, again, has moved from just, from a streaming model, which is small O of n space, to a distributed model with small O of n communication. Okay. And apart from providing job security for theoreticians, models are nice because you can, you can take a lot of your questions now and ask them in these different models, and it changes the very character of the problem. Things that used to work don't work. Things that don't work before work now. And you come up with new widgets that are actually useful, not just in these models, but are useful in other settings as well. And we're going to see that happen for clustering as well. So the problem we want to think about today is to think about how would you do clustering, k-means clustering or k-means, something very, very simple, in such a distributed setting. We've already seen how to do it in a stream setting. Now we want to see how to do it in a distributed setting. Given what you know so far about clustering and how to do clustering at scale, what might you think of doing in this distributed setting?
The string framework that you said before is not like distributed, it's like fine.
Well, all you're trying to optimize space. I'm not saying you can't use the same ideas. I'm just saying that it's a streaming model. But you're welcome to use some of the ideas from there and try to apply them here. What would you do if you're not allowed to send a lot of information back and forth? Do you want to cluster?
So is the data broken up on multiple machines?
Yes.
Okay.
The data is broken up. Okay, so let me be more specific. So your data, your point set, you can think of it as broken up onto multiple machines, and you want to cluster the union. Right? So you want to cluster the whole thing. But each part is only a small piece, and these pieces are divided adversarially, which means you can't really assume anything about how they're divided. It's not like each piece is a random sample. Yeah.
Could you try to, so whatever data set each of the computers has, have them cluster that?
Yeah.
And then you can share maybe like the center with everybody, and then you can try to, each person when they get the center, they can look at how their data looks with respect to all the other centers, and if there's data that looks like it's closer to one of the ones, maybe you can try to send those data points. You don't end up sending the whole set. I don't know.
Okay, so you could simplify that even more. So that every node does its own cluster, and then sends its centers to some server. And then what does the server do?
It looks at those centers and sees how close they are or how far away they are from each other and tries to figure out where.
Could it maybe just, I don't know, cluster them?
That's.
So you could be simpler, you don't have to be complicated. So the first idea that is in some sense inspired by what we've seen before is that every node should do its own clustering locally. Right? and then send its clusters to the server, the sort of central server. One of them has been elected the central server. And that one does takes the weighted cluster centers, clusters them, and then sends the information back, saying, okay, these are the official, sanctioned cluster centers for this data set. And this doesn't require a huge amount of communication. Right? So for example, okay, so let's say you have endpoints, and you want to do k clustering, k-meaning clustering, let's say. So we're not dealing with k-means just yet. What might you do? So you might say, okay, I want to cluster these points into some, I don't know, ki clusters. You cluster these points into some ki clusters, so like that. And then each node sends over the list of the cluster centers and a weight, saying, okay, how many points were attached to this cluster? So this node gets a whole bunch, it gets sum of ki points with weights, and it clusters them locally. And it sends the information back. So the total communication is going to be basically this plus some cost for the weights, so the log factor there. And you hope to get a good answer. Right? You can get some kind of approximation using this. So again, using stuff we've already seen before, the fact that you can decompose things, cluster them locally, and merge them together suggests that you can do something reasonable even in the set. And again, that's the core idea you want to be playing with. Okay, I know that this is a good idea because I've seen this happen over and over again, and actually can prove something more. Now, whether you use override communication, it depends on how well you can partition these things and how much error you're going to get, and there's some analysis you'll have to do there. But let me argue that you can do something that's even better than this. Okay? Something much simpler. In some sense, one of the problems with this approach, and it's not a big problem, but a problem is that each node is doing its work on its own, right? Each node is working very hard to make sure its own clustering is reasonably good. And now this gets to your point, right? So suppose they were divided up so that, one cluster was, one set of points was sort of, okay, let's say my data set looked like this. So I have a data set, and these are the points in my data set. So I have some points here, I have some clusters here, I have some clusters here, and there's a whole bunch of points that are kind of outside. So they're kind of not very interesting to the clustering, or they're not very useful in some way. And one node gets them all, by chance. Actually, they're not outside. They're sort of in the middle, in fact. They get little bits of stuff in the middle. They're not really contributing much to clustering. Right? And so this does all the work, it clusters them very well, and sends the answer over. It turns out that information wasn't even useful, because the other nodes had enough information to do the clustering. So in some sense, the work done by this node has been wasted. Right? And it could have known this if it knew ahead of time what the overall cost of the clustering was and some information about the global clustering. But of course, it doesn't really have that information because no one really has that global information about the cluster. So this idea that you could do quite well if you had some clues as to what the global cost looked like, so you knew how much to approximate in your answer. Like if the global cost was very big, then you know you don't have to work very hard to get a clustering here because who cares, the cost is very high. Or if the cost is very small, you need to work harder here. You can adapt the way you do the sampling or the way you do your own clustering yourself. And so this is the basis of this, one of these first methods for doing distributed clustering that looks like the following. And I'll first, I'll give you the algorithm first, and I'll tell you exactly sort of why it works. Okay. So the idea is the following. So in step one, each node computes sort of just some crude clustering on its own data. Okay? And it computes the cost, so some number CI. And sends, put an arrow here, it sends the cost, so that I, to all other nodes. So it's not sending the actual clusters, it's just saying the cost. That's all. It's like, okay, when I clustered my data, this is the cost I got. Okay, again, whether it's k-mean or k-means, whatever, I don't care, whatever it is. And when I say send to all the nodes, I don't mean everyone sends to everyone. I just send it to a server, the server sends it, so you don't spend n, k squared. If there are k nodes here, you don't spend, well, not k. Let's say there are s nodes here, s servers. You don't spend s squared to send them information. You just, everyone sends to a server and server sends them back. Okay? So now every node has, the node I has information on the cost from all the other nodes. Okay? So it knows what fraction of the total cost it is contributing to the process, roughly. If this cost is very small, other costs are very large, then it knows that, okay, the overall cost is so big, my contribution is not going to be that much. Because we know that you can merge these things and the overall cost relates to the local costs. So based on this, based on the information about the cost it has received, now the node, what it's going to do is it's going to sample a small set of nodes, a small set of points, that's going to act like a core set based on this cost function. Okay? And in particular, it's going to decide how many points to sample based on this overall cost. How it does the sampling is a different story. I'll mention that. I'll explain that in a bit. But it's going to sample a certain number of points based on this cost, the cost of CPR. The more contribution it has, the more points it will send. The less contribution it has, the less points it will send. So now it gets a small set of points. Okay? And now what it does is, so let me see. So what it does, it collects. Sorry. Yeah. So then it sends. What it sends out is the cluster centers from step 1 and the sample from step 2. Okay. Making sure these are all relatively small. Well, this is of course, this will be something like k points here. And there's going to be some small number of points. And that's it. Every node is going to send this object here over to the other nodes or to the central server. And these are going to be weighted accordingly. And again, I'll explain how the weighting works. And that's going to be the core set you use at the server to compute the global cluster. So the only trick here, the only sort of interaction, so we could have done this step right in the beginning. The key thing is that by knowing how much of contribution we paid to the overall cost, we can adapt how many points we need to send over. And that's the key. So let's see. So maybe the best way to do this is to sort of start spelling out in a bit more detail what has to happen at every step. Right? So so let's just first add up. So this is of course just one, just one piece of information here. And then this is just whatever the size of it is. So let's say these centers were BI for this node. So there's going to be BI centers here. And you also send the sample SI, which is SI here. So the total cost here is the cardinality of BI plus the cardinality of SI and the weights attached to it. So we need to make sure that this number is not too big. Okay? And just to give you the punchline, let's see. So let me summarize the entire bound. The amount of the size you have to send out is something like this. So let's say you have d-dimensional points and you want k centers. And there's some error probability term because of sampling. So there's a sampling error rate. Plus the number of centers times the number of servers. And if you do this, what you will get is an epsilon quotient. In other words, it will be a core set such that if you cluster that set, your clustering cost is within a 1 plus epsilon error of the true clustering cost with probability 1 minus delta. That's what we need the sampling term. Okay, so in other words, what this is saying is that if you are able to do all this whole thing, the amount of information every server needs to send, every node needs to send to the server, is going to be very, very small. And when I say this is very, very small, I want to point out that, again, if you ignore this term here, you're going to pay k, that's fine, d is fine. This is sort of like the total size of k objects in d-dimensional space. And you're only paying something in terms of the number of servers. And we'll bring this point up later on, but you can improve this even more. But you are paying nothing in terms of the number of points. The amount of communication is very, very small. Okay. And even in terms of d, it's not very big. The size of k centers is basically something you need to pay. The extra factor of 1 epsilon squared is an error term that you can't really avoid in these kinds of situations. And so the importance of this kind of result is that you actually can do distributed clustering where you have very little communication. It's not just small of n, it's independent of n communication. It only depends on the number of clusters you want and the number of servers you have. And you can actually do so. So once so this is a high-level algorithm. I have a lot of details I have to give you now to sort of convince you that this can work. I'm not going to give you the proofs, of course, but I'll give you some more details. But before I do that, I just want to make sure you at least see how this is claiming to work. Not the correctness, but just the mechanics of how one might try to implement this. So if you have any questions here, this is a good time to ask.
This term is the communication complexity, right?
Pardon me?
1 upon epsilon square.
This is the total, so this is the total size of the course that you need to send over. So technically you might want to multiply this by a factor of d because there are that many points, but this is the number of points you have to send over. So it's not the number of bits, it's the number of points. Yeah, so then this whole thing should really be multiplied by d to get the number of bits. Or d log. And again, the idea is that you start off with some initial clustering, which is which is okay. Use that to do a more adaptive sampling, and send those points along with the original centers, and that's your first step. What's interesting is that first step doesn't have to be very good. Just kind of interesting. You don't have to do too much work. I mean, you need some constant approximation, but you don't need much else. Any constant approximation to the cluster model, of which we've seen a few so far. So any questions so far? About how this things work. So remember, things go out. So you do your clustering, send the cost out, get back the cost for everyone else, because you send them all out, and then use that to bias how you do your sampling the next time. Okay? All right. So what I want to do now is basically tell you how you do the sample. That'll, in some sense, almost automatically tell you how many things you need, but I won't tell you how to do the sample.
What do you do once you have the sample?
Pardon me?
What do you do once you have the sample?
Once you have the sample, you have to weight points in a certain way, and I'll tell you how to do the weighting. And you just send them over. You send them over to everyone else, or to the central node. So every node itself implements an algorithm. So it does a local clustering, sends the cost over, gets the cost back, does some more sampling, and sends a sample. And the amount it sends over is that much.
Yeah, no, that's
This process seems repetitive, right? Like
It's
sending
once.
back or just once.
Well, local cost, number,
Yes. And
get
then
back
send-
numbers,
Yes.
local sample, send sample.
That's all.
That's it. Doesn't have number.
And then you combine all those samples.
The
All
central
those
node just
samples.
takes all the samples, comes here to the computes a single clustering,
Yeah.
and says this is the answer. There's no more back and forth. Right, does this seem plausible as a distributed set?
Sorry?
Does it seem plausible as a distribution? I mean, there are parts of that are quite natural, right? I mean, you could imagine doing this, right? You may not have thought to do the first part, but you can imagine doing the second part. We just talked about that, right? Do something locally and send the answers over to the server and let them do the job. There's an extra step that gives you a bit more fine tuning.
So what exactly are you gonna sample
We're going to sample from our local store.
from our local store?
So every node has its own local store of points, right? Whose union is the entire point set. So I'm going to resample from my set. Well, not resample, a sample from my set.
How do you partition the data initially?
Arbitrarily. So it's given to you. The partition has been given you. So that's the thing. It's a good question because this comes up a lot when I talk about these things.
Yeah.
It is not the case that you start off with a data set, then try to partition it and do all this. No, no, no. That's not what you're doing. You're not trying to parallelize the computation. That's more when you use MapReduce and other things that we talked about. The data is already on separate nodes, and now you have to compute something with it. That's the setting you're in. Right? You're not doing this to improve parallelism. You're doing this because you have no choice. Your data is already sitting on separate servers, and you have to compute them together, and you don't want to copy them over the same. Does that answer your question?
Yeah, it's just like, the problem comes with the second step, because you're gonna sample it in a local node. And if you don't have some reasonable distribution, then you have no idea what you're gonna
But
sample.
it works. That's the beauty. You don't need to know anything about your data. I mean, if you want some intuition, in some sense, the first step is giving you enough very crude information that tells you how to sample in the second step. That's the intuition for why this should work. I mean, your objection is a good one, saying like, why should this work? There's no reason why it should work if I have arbitrary data. And the answer is kind of. Because I get some rough information from the first step, that turns out to be enough to do the sampling okay in the second step.
So I have a question. Is it possible? Let's say you have cluster. The data is clusterable, and then you
Sure, it's good, it's well clustered.
and then you somehow accidentally store it
So that it reclusters on one.
on machines in such a way that it's not clusterable locally.
So you sort of
It looks almost like random.
Okay, so in other words, maybe you put one cluster on each node. Because I mean, if you have very well clustered data, it should look like a bunch of clusters
Yes.
that are themselves kind of random. There's no way to divide them any further. Okay, and then you put this on one node. So now it has no structure in and of itself. That's your case.
Sort of, yeah.
Yeah. And so now what's your objection? So what causes? So where do you think this might cause a problem with this whole process?
Oh, I don't know the second step yet.
Right. So let's talk about the second step, and then we can sort of evaluate what's really going on. Okay. So here's the idea. What we're trying to do. Think of this a little bit more abstractly for a second here, because again, there are lots of details here that are intricate enough that I don't want to get into them. That I think are just detract from understanding what the intuition about what's going on. So I want to give you a kind of a high-level view, and I'll link to the paper that actually talks about this in more detail. So let's say I have some function, okay, and I have a point set, and what I want to do is compute the value of the function summed over all points in the set. Okay, that's what I want to compute. If you're wondering where I'm going with this, you could imagine f is the k median cost for a single point, at the distance from a point to its closest cluster, if you want to think of it. But this is what I want to compute. So there's some kind of sum. So again, you can think of this as saying I have a bunch of points. They all have weights. Each weight is the fp. And I want to compute an estimate of this value. Okay? And I want to sample. So what might you do? You might say, okay, I'll take a uniform random sample. And very quickly you'll realize this is not going to work. Right? Why would a uniform random sample break to compute that function? This is a good exercise to think about, right? So if I want to take a random sample of the data to estimate this property, let's say I'll just pick every point uniformly at random. Why is that going to break here to compute that? Forget clustering, forget everything else. It's a very simple randomized sort of sampling question. What goes wrong? I mean, you can prove it, but there's a very intuitive reason why you can't just do a blind uniform sample. So what do you think will happen if I just do a
sample, remove some of the terms in the sum completely?
Now I'm saying I just have a bunch of points, and I want to estimate this property. So I'm going to just take a bunch of points at random and add up their values and scale it accordingly. So I'll take a sample of size R, add up the FP values for those points, and then multiply it by, so just, and scale it up. Something bad is going to happen, right?
Is it independent of f, function f? I mean,
Are you asking the question or are you
yes,
pointing
yes,
out a
I'm
problem?
asking the question.
What, so the sampling is independent of F, yes. The one I'm just telling you right now.
So it
The one that I claim will not work.
something bad in random sampling.
Yes.
If f is linear, it works, but if f is very heavily dependent on it's non-linear.
So can you explain what's going to, can you give me an example of what will go wrong? Can you just give me an example?
You just you put
Give me some values.
some 1 to k, right?
You might have very big FP.
Right, so let's say this value is 1,000.
Yeah.
And every other value is 1. And let's say there are 100 things here. Okay? Let's make this 10,000. So is any kind of uniform sampling going to get me the right value? No, because with high probability, I will never pick that one element. I'll just add up these values, and they won't tell me if the actual value is very big. Okay, I know some of you are wondering why I'm making a big fuss of this. That's kind of obvious for some of you. But the point I want to make is that you have to do some kind of weighted sampling. You can't do an unweighted sampling of the data, right? And what you'd like to do is sample with a probability that relates to the actual F value itself, right? So here's what you want to do, right? What you want to say is that I'm going to pick some sample S, not S, pick some random point R belonging to P with probability FR divided by, let's call this right? That's kind of what you want. You want to pick the points that are heavier with more probability. Okay. And then what you're going to do is, and you're going to define its weight now, okay, to be 1 over F of R. 1 over F of R or S over F of R? Sure. It should be S over F. We'll figure out what this is. I think it's okay. And then I'm going to say, okay, so pick R1 up to RT, okay, with their weights in this thing, and then compute their weighted sum. So I'm going to compute, let's say, this is subset T, sigma R belonging to T, weighted R times F of R. Okay? So this weighted sum is going to be my estimate for the true sum. And again, if you're wondering where I'm going with this, again, imagine this was actually the clustering cost. What I'm saying is that I want to compute some random sample so that the cost of the clustering of the random sample is close to the true cost. In other words, it would behave like a coarset. So I want this quantity to be close to that quantity. In other words, this is a random value. I want the expected value right, of sum of WR, F of R, to be close to, right? And then the question is, okay, what is the, how am I going to do that? So I can rewrite this, of course, as this is the sum over all R belonging to capital set T of WR, expected value of WR F of R. Okay. And you can rewrite this expression as saying that this is basically on to P, probability that R is equal to P times WP times F of P. So in other words, it replaces expectation by the actual definition of the expectation, which is the average value over all this. Okay? And now you kind of see where I'm going with this. What's going to happen is that this quantity here is going to be sigma R belonging to T, sigma T belonging to P. We know what this is. We just said what it is. It's going to be that. So it's going to be F of T over S. Okay? And this weight is going to be 1 over f of p, right? What is? Oh wait. That doesn't make sense. Yeah, so this weight should be, I think, should be,
S over.
I think it should be, this. Okay. I think I need another term here. Yeah, I need another term. So it's going to be here. This is going to be t. So this is going to be sum of r belonging to t. Cancel, cancel. It's going to be fp by t. So in other words, if I pick points with this weighted probability and give them a sort of a reverse weight, again normalized by the number of points I pick, then the expected value of my estimate here is in fact the value I want. So this is an unbiased estimator of the quantity I'm trying to figure out. And I need only t points to do this. Well, I say only t, I'm told you what t is going to be, but I need t points to do it. Right? The hope is that t is very small. But this is just at least saying that the expected value is matching, which is the first basic property, right? You want the expected value to be unbiased. Now we can apply our Chernoff magic. So it's, okay? Does that make sense? And so, again, what's left to show is that you can make this t small. And again, the intuition is that somehow you need to know, the basic idea is you need to know how variable these values are. Right? We know that if the values don't change very much, then things are okay, because you can sample out almost as if it's a uniform distribution. But if the function values are very skewed, then you have to pay attention to the max value. Right? So look at the worst possible value, and you have to control that. So to cut a long story short, what you can show is that if you set t to be something like so you need something like, and this is one of these VC dimension bounds, some constant over epsilon squared times the, I'm going to put in quotes here, the dimension of this function. And again, if you've taken the machine learning class, how many of you have covered VC dimension already in the machine learning class? So you've covered it. So you're probably familiar with bounds of this kind, right? There's a VC dimension term and a distinct term if you want to get an approximation. It's the same property here, except that this is not a range class. It's not F is not really a concept class in the usual sense. It's a numerical class, but the same basic idea works. Okay. And again, this is a technical detail I don't want to get into right now. You can define a notion of dimension for a function class that says that this whole sampling trick works. And in particular, for things like k-means, this quantity is something like k times s. Okay. So roughly t equal to 1 over epsilon squared k times, maybe not s, d, k times d. So it's roughly t, something like k d over epsilon squared plus 1 over squared log 1 over delta for a high probability bound. Number of samples, you get what you want. Okay, and you get, in other words, what you get is a good, that with high probability, the answer you get from here is within epsilon of the true value. So we've already said the expected value is the same. What you want to say is that with high probability, the tail is not very far. So with high probability, then we expect this value here, sigma wr f of r, is not going to be very far from the true value s. It's going to be less than or equal to epsilon times s. Okay, so it's within some multiplicative factor. Does that answer your question? Now that we know what it was something.
We still don't know how to pick those with that probability.
Yes, very good. That's good. I'm not done yet. I haven't told you what f of r is going to be. Let f of r is some magic function. So how do I pick FMR? And here's where the information from the other nodes comes in.
Oh, we can approximate S for
Yeah. So here's what you're going to do. You're going to do two things. First of all, we need to know what f of r is. What is this quantity f that we're going to try to compute here? And what is it going to be? This value f is going to be the following quantity, or the proxy we're going to use for that. We can't actually compute f because we don't know the true clustering. But it turns out that if we replace f by the distance of fp by a distance of a point from its current clustering, call this mi. This is going to be my proxy for the actual function value. So what am I saying is the following. What I would like to do is say that this function value is the distance from the point to its cluster center in the true clustering, because then my estimates are good. I don't have the true clustering. What I do have is my own clustering that I did on my own data, so I'm going to use that value instead. So in other words, I'm going to compute the mi and I'm going to normalize them to get the problem. So I'm going to sample with respect to the mi, not with respect to the f that I don't actually have. So that's step one, to make this actually work. Step two is that the t I'm going to pick, and again, it depends on the function value, right? The t I'm going to pick is, as I said, it is basically what do I want to say here? Right. So the total number of points I want to sample is this much. I know that. Right. If I had some global data set and I want to sample points, this is what I would sample. Each piece has its own little patch of the data, and each patch has its own cost. So for each set, I'm going to sample a TI, which is basically T times the fractional cost. So the cost of BI divided by the total cost over all servers. BK over all G. Okay, so what's going on here? Remember that I said that if I want to sample, I need this function value and I need this T value. Once I have these things, I can sample the estimates quantity. But all of this is distributed now. So first, I don't have the function value. So I say, okay, fine, I don't have this value. I replace it by my proxy, which is my local distance to my best clustering. It's not great, but it'll do. Secondly, I don't have the total T value. I can't do over that. But I know what fraction of the total clustering cost, or at least I think I know, what fraction of total clustering cost I am contributing. And I know what the others are contributing. So I sample that many fraction of points. Okay. So in my algorithm now, what I'm saying is that once I get the information from all the other nodes saying how much their clustering cost was, the smaller mine is, the fewer points I have to sample. And I sample using this rule. And I send all that stuff over with the appropriate weighting. There's another technical detail about how you weight the original cluster points, but again, it's not very relevant. And this is your distribution. So hopefully I've given you a little bit more information on how you do this thing and how the information in the first step influences what you do in the second step. By basically controlling how many sets, how many elements you pick. So in some sense, you're running what is this abstract. So you have this kind of high-level algorithm, which is saying, okay, I have these points, I sample a bunch of things from them, and I use this estimate to give you the full answer. And now I'm saying, oh, wait a second, I don't actually have access to all the data. My data is broken up into pieces. So I want to run essentially this algorithm in a distributed way, where the size of this piece corresponds to how much contribution I was making locally to the cluster. And that's what this algorithm is doing.
So if a local cluster, if you consider a cluster in a single server, which is P1, P2, then if the cluster is well formed, then it does not contribute much, right? Because
yes.
the cost will be less, and then the number of sample points will be less,
right.
and it does not contribute. So how does it make sense then? the cost is less, then it does not contribute much to the final clustering.
Because if it's not contributing much to entire clustering, why do I need any information from this to compute the overall clustering? In other words, another way of asking the question is this. So look at the overall clustering cost. So let's say the overall clustering cost is C, and it consists of everything else plus the cost from this node. And I'm saying this number is small. Okay? So I'm really, it looks more like this. Okay? If I don't get a good estimate of this, what do I care? What I really need to care about is getting a good estimate from the rest. And that's it. But I don't know ahead of time how much information, how much contribution I have, which is why I have to do this local clustering first. The magic somehow is that even if my data sets were divided in some arbitrary way, and I look at that cost value, that's good enough. And that's basically because this whole merging process is agnostic to how you merge.
Kind of Amdahl's law.
Sorry?
Amdahl's law.
Is it really?
Yeah. Kind of. Don't focus much on that part where you cannot get much.
Oh, I see. Yeah, okay, I see what you mean. Yeah, okay, good point. Yeah. Did you have Natalie, you have a question? Okay. So, right, so that's the intuition as to why you don't care about this little piece. The magic part here, which I have not mentioned, is why, like I said, the local clustering you're doing is enough to give you a clue for how you contribute to the actual clustering. And that seems very non-obvious. Why should my local data be a good representative of the global data if I divide arbitrarily? It turns out it does, and that's why this paper is kind of interesting. It shows that this works. And again, the intuition for why it works, in my view, and they don't say it that way, is that when you do this kind of cluster merging, it doesn't matter how you divide things into groups. Somehow any group is okay, and the results still work. And I think that's the leverage that's being used here. Like clustering is a nice problem in that sense. You can partition things in any way you want. They still kind of merge together, and you can estimate cost. And that, I think, is a very good intuition to have about clustering. At least for things like for these sum-based measures, like k-median or k-means. For k-means, by the way, this gets a little bit more technical, because certain triangle inequality things don't work. So k-median is the easiest one to think about here. But the basic method is still the same. You just change these weights a little bit and get the papers. Okay, any questions before I move on to the next piece? So this was a way of doing distributed clustering. It was a very interesting way, and it exploits again the idea A, that you can merge things together in clustering, and B, that you can compute these small core sets and send around the core sets rather than sending around the actual data. And one thing that has happened in the last few years, 4 or 5 years or so, so this is something that Jeff has spent a lot of time thinking about as well, so you should something you talk to him about, is that thinking of data as a matrix problem turns out to be very effective. That there are a lot of things you can do if you reformulate a problem as a matrix problem, because you can do matrix sketching. That's something you're in class right now looking at this. There's lots of nice things you can do with matrix sketches. And so it turns out that you can do even better than this for clustering problems if you reformulate your clustering problem as a matrix problem. And this only works, I should say, for k-means. It doesn't work for other clustering problems. But it's so useful, I think, that it's worth knowing how to rethink of a clustering problem as a matrix low-rank estimation problem. Because then all the machinery of low-rank estimation allows you to do things very well, especially at scale. So I want to spend a little bit of time explaining that connection. I think it's a connection, first of all, I didn't really fully appreciate till I saw it being used over and over again in papers to get better and better results. And so I want to share that idea with you, and then hope to show you how using that idea you can now take this heavy hammer and start applying it to these problems that you wouldn't normally have been able to do. So some of this paper did a lot of work to do clustering. So we do sampling, we do this. Once you think of this as a matrix problem, you can just apply all the matrix machinery and automatically get results for free. And we always like getting results for free. So. Okay. So let me move on to that stage now. And this will be the last sort of bit I want to say about clustering at scale. Next week we'll talk about outliers and other kinds of interesting modeling issues with this. Okay, I'll leave that there. Okay, clustering as a matrix problem. So let's see how we can set this up in an effective way. Okay. So just a reminder, the Frobenius normal matrix. How many of you are taking Jeff's class right? 1, 2, 3. Okay. Sure, let's Frobenius normal matrix. Take out your this. Hmm? I'm gonna tell her. Now if I ask who else is taking just class, I won't answer it. Thankfully, I remember. Right, Jan, you take a hack at this?
Yes, it's sum of the aij squared.
Thank you.
Oh, the definition of Frobenius now.
Hmm?
Yeah.
Too late now. She already said that. The way I like to think about this is just treat your matrix as a long vector and take its L2 norm. Frobenius norm is the L2 norm of the matrix treated as a gigantic long vector. Okay, so okay, just for me to keep it. All right.
Isn't this something related to the trace of the matrix? It is, right?
You can. You could write it as the trace of.
A transpose or something. Or he's in another.
Yeah, sure. For some problems, it turns out to be more useful to write it that way. For some problems, it depends on what you mean. I get to find a good intuition for the trace, geometric intuition for the trace. Is there one?
No.
Yeah. Or maybe there are too many. It depends on the problem.
Yeah.
Yeah. Because sometimes it's a product, sometimes it's something else. All right. So let's define the following problem. I have some matrix. So I'm given some matrix n cross d, and I'm going to write it this way because I want you to think of this matrix as a collection of points where each row is 1 point. Okay. That's why it's n cross d. So you speak properly as. All right. And what I want to do is I want to compute. So given some set S of rank K orthogonal matrices. Okay, so these are rank K orthogonal matrices. I want to find so these are rank K orthogonal projection matrices, I should say. So in other words, a fancy way of saying this is that if S is the collection of all rank K orthogonal projection matrices, then this is what? What am I trying to do here? So think of this as some kind of error term. I have the original matrix A. I have now modified it by doing this operation, this projection operation onto rank K. And I want to make this number small. So what is a more familiar way of saying this?
Minimizing the error.
But of what?
Frobenius norm.
Sorry?
The Frobenius norm of the difference of these two.
Yes, yes. But what is that? What am I, at a higher level? This is a more familiar problem that you've all seen before. I'm trying to find a low rank matrix approximation. Right? This object here is my low rank matrix approximation. So the way of saying this is I want to find the projection that will get me that low rank matrix approximation.
Why
Okay.
Frobenius not?
Because in a second you will see why. Okay. I mean, I should say that as a general problem, there's nothing wrong with Frobenius norm. It's a perfectly reasonable norm. In fact, this is what will give you the SVD. Right? The SVD will give you exactly this.
It's also the easiest to work with.
Yeah, because you said. But it's going to be very useful for a second. And I want to emphasize here, I am not, okay, so if S was all rank K orthogonal projection matrices, the solution to this problem is the SVD. Okay? But S is some subset. So if S is all such matrices, this gives us the SVD. In other words, if you compute the SVD of A, that tells you what the projection needs to be. But you can read it off from A. It'll be basically the V part of that matrix. But in general, I might have some other constraint. And so now let me show you how to put k-means in this. This is what makes it kind of cool. So once again, I have the k-means points, right? I have P1 to Pn. These are all in d dimensions. So let me assemble there's unfortunate notation clash now because I don't want the P. So let me just re-notate the points as A's so I can call them an A matrix. So I have I should have written that here as well because now I have P. So I have this A matrix, so it consists of A1 to AN. Each is an element of Rd. Okay. And let's say I cluster them optimally, right? And I have some cluster centers. So let's say I have cluster centers mu1 through mu k. So that mu I is the centroid of all the points assigned to cluster I. Okay. In that case, what am I trying to optimize now? I'm trying to optimize the sum over all points I equal to 1 to n. The sum over all, not the sum. This one? Oh, sorry. Let me do a sum over all over clusters. Sum over all j, over all aj belonging to cluster I. The L2 norm squared of aj minus mu I. Right? So for every point that belongs to a cluster, measure the distance to its corresponding cluster center, add them all. I want to minimize this quantity. Right? So this is, so to minimize this is the k-means objective. Okay? Yes? Okay. So now, here's the cool trick. So let's construct a matrix. So this, let's say this is some clustering. And so let's construct some matrix XC. And this is going to be a cluster indicator matrix. So this matrix is going to be, it's going to be in the, just for R n cross k. So it's going to be the obvious thing. For each point, so for point AI, it belongs to cluster G. So you put 1 there, and you put 0, 0. Then for all the points in cluster J, there might be this point here, and then cluster I might have a point here and a point here. Okay, just to indicate it. And I'll change this a little bit. So I'm going to say that XC ij is not a 1 if AI belongs to Cj. It's actually going to be proportional to the size. It's going to be 1 over square root of the size of G. And again, this is for normalization purposes. So if this cluster had 3 points in it, then each of these values is going to be 1 over square root 3, 1 over square root 3, 1 over square root 3. Okay? And I'm going to do this because I'm now going to ask you what this quantity is. So what is this quantity?
A is n by d.
A is n by d. XC is n by k. So XC transpose is n by n. So this resulting matrix is an n by d matrix. So yes, it's a collection of points, which is a clue. So it turns out, and you can work this out, just a bit of algebra, that in this matrix, the ith row, okay, is going to be the coordinates of the mu j, which mu j? Such that AI belongs to cluster CJ. So the ith row is going to be the coordinates of the particular centroid that that point, the ith point, belongs to. So there's going to be duplicates there. And again, this is just a direct calculation. That's why you need the square root, by the way. This gives you that. And this, essentially, the square root multiplied by itself gives you the size of CJ. That normalizes the coordinates of the points. Because each mu j, remember, is going to be the centroid. It's k-means after all, right? Each mu j is going to be the centroid of all the points. So that's why this whole thing works. Again, you can work this out. Okay, but if that's the case, we can rewrite that quantity. Right? Because now, you can rewrite this entire quantity as this cost as the Frobenius norm of A minus XC transpose A. That's why we use the Frobenius. And lost my battery. That's not good. Almost everywhere.
Do you need this charger?
Huh?
Do you need this charger? I can give
No,
this
but
charger.
I need the MagSafe part 2. Oh yeah, that one will work actually. That's cool. Yeah. Okay. So my method is helping with that. So what I'm saying is that because the ith row here is the coordinates of mu j, by subtracting I'm saying, okay, take the point, take the difference to that corresponding cluster center and just square them all. That's what you're going to get from this. So I have rewritten the k-means objective. Thanks, Lord. Hopefully, only 20 minutes. So hopefully your battery won't die.
Yeah, it's charged.
So what I've done is reformulate the k-means objective as a Frobenius norm, but it gets even better, right? Because now, if you look at the form of this expression here, it's not hard to see that this matrix is orthogonal. It's also not hard to see it has rank k. Why is it rank k? Because it is in cross k crossing cross k. It will only have a rank. It's only a rank k matrix. Right? I'm not going to increase the rank just by magically multiplying by itself. So this matrix is of rank k, and it's orthogonal. So minimizing this over all such matrices, the XC transpose matrices, is in fact doing exactly this. And now you see why I said I have some arbitrary set. It's not the whole thing. It's a specific set of matrices formed in this manner. Right? Not every rank k orthogonal matrix will look like that. But these will all be of that. So you can think of k-means clustering as a problem whose relaxation is the SVD. But it's actually a constrained version of that. Okay? So in other words, k-means equals to constrained SVD. Or SVD is a relaxed case. Okay?
That's what makes it much harder.
Sorry?
That's what makes it harder.
The constraining. Yeah, that's right. Okay? I should say that, I've seen this being used in papers before,
Can you
but I never appreciated how nice it was, like sort of finally got it. And like I had to teach it and sort of and think about really what's happening. It's a very cool trick. Yes.
Can you complete SVD and then approximate the...
Indeed, and that's exactly the point. That's what I want to. Yes.
Maybe Woman just asked the same question, but could you find P and then find the XC that when you square it gives you P?
You're not going to do it directly, but essentially it's what you're going to do. You're going to say, look, I know how to do SVDs really well. I should be able to do this. And that's the magic of what you want to do here. By reducing it to matrix form, use all the magic of matrix analysis to help us here. This is why I have to apologize for all the years I spent complaining about matrices. They're really helpful. Okay, so, but before I do that, I want to point out now that you can actually do something a lot better. So here's what we're going to do. I'm going to introduce a new notion of a core set designed for these kinds of problems, for matrix problems. And that new kind of core set designed for matrix problems is going to help us with our clustering problem. So what is this new kind of notion? So these are called projection, they're sort of a mouthful. It's a rank K projection cost preserving sketch. That's an annoying statement here. But let me try to explain what I'm saying. So I have a matrix, which is n cross d. What I'm going to compute is some kind of sketch of this matrix, some kind of approximation of this matrix. We'll call it A tilde, whose dimension will be n times d prime, with the idea that d prime is going to be much, much smaller than d. Okay? With the following property, that whenever I want to compute this thing here, and I replace A by A tilde, it doesn't change things very much. In other words, if I take any projection matrix and I look at this cost, and I'm going to assume this Frobenius norm from now, and I don't want to keep writing it out. Well, maybe I should. It's going to do the usual thing here. I'll put the thing in the middle at the end.
Yeah, but you can again use SVD to do that.
Pardon me?
You can again use SVD to do that.
Oh, no, yeah. And in fact, I can. That's right. Okay? What I'm going to put in the middle is this. So what I'm saying is that if I take my matrix A, for which I want to compute this constrained low rank approximation, or any low rank approximation, and I replace it by this modification of this matrix here, which is much smaller, then I can use it as a proxy in my minimization, because for any P I look at, any projection, the costs are more or less the same, up to some small amounts. And of course, as you point out, this is kind of dumb because that's what the SVD does for you. The point again is at scale. SVDs are hard to compute. But if you can compute some sketch matrix that has SVD-like properties but can be computed efficiently, you can do all this. And again, before I go any further, why do I care? I care because if I can do this for every matrix P, I can in particular do it for all the matrices P in my subset S. Right? It's true for everything. It's true for them. But if I can do it for them, then I can do it for this. So in other words, what I'm going to do here is somehow reduce the dimension of A, and then run whatever algorithm I want to run on it. But what does that mean? What is happening when you go from here to here? N has not changed, but D has changed. In other words, this process of computing a rank K projection sketch, this object A tilde, is a dimensionality reduction. It's reducing the dimensionality of the data down from its original dimension, whatever it was, to something much smaller. And to give you a sense of how much smaller this will be, it's going to be something like, K over epsilon. Something that depends only on the number of clusters. So what this is saying is that there is a way to reduce dimensionality of a point set from its original space down to K over epsilon, where K is the number of clusters I want, and then epsilon is my error term, such that if I look at this reduced dimensionality data, I can run whatever clustering I wanted, and it will be good by this argument. So it's not a core set in terms of taking a subsample, it's a dimensional reduction in terms of reducing P. So when I teach geometry, I often say, right, when you have a high dimensional problem, there are two ways you can deal with this, right? You reduce this or you reduce this. This is core sets, this is dimensional reduction. We've talked about core sets before, and now I'm talking about dimensional reduction. And there's no reason you can't combine them. Right? You can do this first and then do this. So you can get things that are independent of D and N. And that's a very powerful tool. So if you remember this kind of basic idea, for any problem, these two tricks allow you to do all kinds of magic to get rid of any dependency, or almost all dependency, with some error. So the basic idea is now, if I have a way to compute the sketch efficiently, then I can do clustering efficiently. And in particular, if I can do this in a streaming distributed whatever fashion, I can do clustering in a streaming distributed whatever fashion, because I have this property. Okay. And again, I'll cut to the chase and tell you, how you might go about doing this. Of course, the easiest way to do this is to just project A onto its singular vectors. So the easiest method for computing this A tilde, so we'll call it method 1, is equal to A projected onto the K over epsilon top singular vectors. Right? So if you think of A as U sigma V transpose in the SVD. You take the top, let's say, take the top K over epsilon of each of them. That's my A tilde. And effectively, the way to do this is to just compute these guys and compute A times V. And that'll get you what you want. You'll get your distribution. And that's all well and good, except that we would prefer not to have to compute SVDs because they're a pain in the neck to compute, especially when you have things distributed. But here's the thing. It turns out this result is very, very robust. Even if you can't compute the projection exactly, and you can only do it approximately, it still works. You get some little bit more error. You get a little bit of error, extra error here, additive here, and here, based on this. Oh, I should have mentioned this one extra term here, which is actually very important. Some extra additive constant here. That actually is very important. I shouldn't have forgotten that. Without it, you can't do this. You get some extra error terms here. It still works. In other words, if you can compute, if you have some approximate SVD, it still works. Specifically, let A tilde be any low rank approximation of A that you can compute any way you want. Right? Then this bound works in terms of the Frobenius error. So this is a very robust result. And this means basically you can apply all the technology from matrix sketching to get, which is built around the idea of how to do these things, and apply that here to the cluster. There's a nice sort of sub-result that is in this one particular paper that does all this shows here, which is worth mentioning just because it's kind of cool. That it says that if you do a random projection, so this is like what is called a Johnson-Lindenstrauss projection. I mentioned Johnson-Lindenstrauss projection before. You take a random Gaussian, you multiply by data, and you just project it down into log k over epsilon squared dimensions. So even better than k, log k dimensions. It turns out you can show that this gives you roughly a 9 approximation. It's actually 9 plus epsilon. 9 approximation to k units. So all of this technology is basically saying things like, take your data, randomly project into some very small space, and then do clustering in that small space. So there's been a lot of folklore about k-means, that somehow I only really need k dimensions to worry about k-means, because k clusters are also like k dimensions. I don't need much more information. And this result basically says that if I project onto k over epsilon dimensions, that has enough information to give me a good k-means result. But this is something even better. If I project into log k dimensions, I can get a good result for k-means. And again, it comes from these kind of matrix arguments. And again, I won't prove this problem. I'm not proving it, but I definitely won't do it. But this is a bit more tricky. But the importance of all of this, going back to our initial story of distributed clustering, is that this tells you how to do distributed clustering another way. Because what it says is that to compute this approximate SVD, one way to do it is to do a certain kind of random projection. So you take a certain matrix, you take a random matrix R, and you multiply A by R, and this gives you some A tilde. And this is carefully chosen from some distribution over Gaussians, and this all works. But what happens if your things are distributed across multiple nodes? You can think of this matrix as kind of stacked up, right? So you have A1, A2, up to AS for the S servers multiplied by R. But that's the same thing as saying that each of them individually gets multiplied by R. So your new algorithm for doing distributed clustering is not to sort of have everyone do something locally and send their core sets over. It's to first have the server tell them, hey, do this random projection. Which you can tell them very easily because this is just a function. There's no data. It's just a function that says, okay, run algorithm number 5 from this paper. Or something very short. You can just describe it. Okay. So they all run it locally. They get a much smaller set because I've done this projection down into a much smaller space. And then send a core set built on that. So you can actually put all this together. It gets a bit messy, but you can actually get formally better bounds than what you would get with the previous method I mentioned. And again, the idea is that you're using this matrix approximation to reduce the space even. Okay. So that's all I wanted to say. Again, it's something I thought was very cool, so I thought I'd just tell you about this. That that the matrix inside, and if you remember nothing else, just remember this, right? This matrix connection to k-means, and only for k-means, as you can see why, you need all this nice squared and stuff to its work, is very powerful. It gives you bounds that you would have been very hard pressed to prove some other way in the streaming setting, in the distributed settings. Okay, I think that's it for today. Any questions before we? So like I said, this is going to be the end of our discussion of scalability. In the next few lectures, I'm just going to move back to other modeling issues related to clustering. So for example, how do you do with outliers? What do you do with soft clustering? So things like that. If you don't want to have hard assignments, or you only want soft assignments. So if you have any questions, you can otherwise we're done. Okay, good. See you all next week.